Okay, welcome to Computer Networks. This is lecture 20. Just wanted to remind you that the homework is due today or tomorrow, depending on the schedule that you selected for yourself. Homework 10 is already out. And we already talked about homework 11 and 12, right? Okay. And there are some student presentations happening today. If you're interested in presenting a topic, please come talk to me. Just one other quick announcement about the homeworks. What we're going to do is make one of the homeworks optional. So what that means is, let's say you submitted 12 homeworks. We're only going to count the top 11 homework scores for you. So if you've done well in 11 homeworks, you don't need to submit the 12th one. Does that make sense? Any question about that? But if you had a bad time one of the weeks, then this would be a good way to make up for that. Any question? Or if you have a very busy last week of the semester, then maybe you can skip that if you've been doing all right in the homeworks. Okay. Homework 9. Anything you want to share? Any concerns, questions?
I have a thought on the DHCP stuff. I'm not sure if I'm getting the right results.
Okay.
Because I counted 700 something packets for DHCP.
Yeah.
There's only like 6 distinct packet sizes.
Uh-huh.
Does that sound right? Or
that sounds all right, yeah.
Okay.
So one of the concerns was there were only few distinct packet sizes for DHCP. And if you observe that, that's what it is. Anything else? We're able to draw CDF. Yeah, okay. If you're still confused about CDF, you can go to the video from a couple lectures ago to see what it's about. Any other questions? Did you get a chance to look at homework 10? No? Okay. All right. So please ask questions if something is not clear on homework 10. All right. So today we're going to wrap up our discussion of the link layer and talk about a few aspects of the physical layer. I'm not going to focus too much into that. But it's important to understand at least a little bit about the physical layer for us to understand the networks. So this is the model that we used last time. We have nodes connected with a bunch of wires. That is what we started with. And we said it's going to be hard to manage these cables as well, for example, from organizational perspective, and also to scale them. So we introduced these boxes called bridges or switches that connect networks that are organized into segments. A segment is a wire or part of the network that has multiple computers connected to it. One of the problems that we run into when we organize our networks in this manner is knowing where a particular host is. For example, let's say a packet comes across the internet to a particular network, and let's say we have that network organized into multiple segments. We need to know the segment on which that host is so that we can deliver the packet, right? One way to get around that is by having the bridge broadcast the packet to all the segments. That'll work fine, right? What's the problem with that?
You're not really gaining anything.
Yeah, you're not getting much at that point in terms of separating the segments so that you can have multiple communications at the same time, for example, right? We don't want to forward a packet where it is not needed. We want to minimize the time we use a particular segment so that legitimate communication can take place at that time. In order to do that, we need to know if a particular recipient is on that port, or we need to know if a recipient is not on that port to make that decision. And one approach is to learn hosts' locations based on source address. For example, that bridge, let's say sometime in the past, received a message from node Y. On what port would it receive that message? Port 1 or 2? Port 2, right? Now, let's say at some point in time in the future, there is a packet that comes into that bridge with the destination Y. On which port should it transmit that packet? Port 2. So this is called building a table as you receive packets. So that's great. Now we know where to transmit a packet or where not to transmit a packet depending on how you're designing that box. Now this allows us to scale our network to a sizable network. Not just 5 or 10, but perhaps hundreds within a campus, for example. Most of the corporate networks these days are switched networks. Okay, so that's great. But one of the problems that we run into when we start adding switches in our network is a potential loop. For example, we might make it possible without our intention, unintentionally, for a packet to go around in a loop. As we saw in this slide, there is a loop consisting of bridges 1, 4, and 6. Does everyone see that? Yeah, okay. Now, why is this a loop? Do people remember? This is the discussion we had towards the end of the class. Why is this a loop? Can you give me a scenario that shows this is a loop?
A broadcast comes in on J,
Yeah.
and B4 receives it, and it's a broadcast, so it sends it to H and I,
Mm-hmm.
and so B1 and B6 both receive it.
Mm-hmm.
And then it's a broadcast, so B1 sends it out on all of its interfaces except H, where it received it from, but it sends it to G.
Mm-hmm.
B6 also sends it to G.
Mm-hmm.
So then B1 and B6 each receive the other one's broadcast, and they both send it back out to B4,
Mm-hmm.
and it ends up multiplying and taking up more and more of the.
Yeah, so does everyone understand that example? Because we're not remembering which packet we forwarded, right? We don't want these boxes to be too complicated. Right? So let's say a packet comes in to B4, it's going to just saying the example again, packet comes into B4, it's going to transmit on both the ports, B6 is going to receive it, it's going to transmit on both the ports, or I guess in this case it's going to transmit to 1, and 1 is going to think that, oh, this is a different packet, it's going to transmit back to B4, etc. Right, so we have a loop. And we said there is a way to address this problem. Does anyone remember what that technique is called? Spanning tree is a spanning tree. So let's read this paragraph from Wikipedia. In the mathematical field of graph theory, a spanning tree T of a connected, undirected graph G. So what is a connected graph? Let's sort of parse all the words here.
You can get to all the nodes.
Yeah, so that means you don't have a node that's not connected to anything else, right? So all the nodes are connected by at least one or multiple edges. So that's called a connected graph. So you don't have two different graphs disconnected. What is an undirected graph?
It means each connection is two-way. There aren't any connections that can only be used in one direction.
Yeah. So in networking, an undirected edge would be a link on which you can transmit information in both the directions. Let's say we have a cable connecting A and B, where A and B are hosts. It would be an undirected edge, if we're trying to represent that as a graph, if A can transmit information to B and B can also transmit information to B, not necessarily at the same time, but they're able to do that. Okay. Spanning tree T of a connected undirected graph G is a tree composed of all the vertices. So we know what a vertex is. Right? In the context of the network, again, it's a host. And some or perhaps all of the edges of G. So this is interesting, isn't it? It says some or all of the edges of G. Why that distinction? Because sometimes in a graph, there might be multiple ways in which nodes are connected. It turns out it is adequate for a graph to be a spanning tree if there is at least one way in which the edges are connected, right? Informally, a spanning tree of G is a selection of edges of G that form a tree spanning every vertex. So we have a graph with lots of links. It turns out we want a graph with edges that touch all the vertices in the graph. That's what we're looking for. Why are we interested in covering all the vertices? Or in the language presented here, spanning all the vertices? What?
Make sure that we can reach all the hosts.
Yeah, because we might want to send information to any node in the network, and we need to be able to do that. And that's the reason there has to be at least a path to reach all the nodes, right? That is, every vertex lies in the tree. So this tree that we're going to abstract from this graph, it needs to contain all the hosts, but no cycles or loops. So usually when you have a loop, what is the minimum number of ways you can reach a particular node in that loop? Two, right? Turns out we don't need that in the spanning tree. If there is one way to get to the node, that's enough. All right. So let's look at this graph. So we have a bunch of vertices, 1, 2, all the way to, how many are there? 9, right? And we can see all the edges. So the question is, do we need all these edges for us to be able to send a message from one node to any other node in the graph? That's the question. And if there are more than one ways to send a message, then that's not a spanning tree for that graph. That's what we're talking about. So are there more edges than necessary? That's the question we should ask. There are, right? For example, let's say 1 needs to send a message to 2. Well, it can just send it directly, or it can send it through 1, 8, 5, 2. So there are multiple ways for a message from 1 to get to 2. So this is clearly not a spanning tree. This is a spanning tree that we can construct from this graph. If you look at the red lines and the red nodes, the nodes are going to be exactly the same as the original graph, right? Because we want to be able to send a message from any node to any other node. The edges on this tree are colored in red here. So let's look at this graph and convince for ourselves that there is a way for us to send a message from any node to any other node in the network. Let's say we want to send a message from 6 to 5. Can we do that on the spanning tree? What's the path? Can someone tell me? Let's say we want to send a message from 6 to 5.
6, 9, 3, 1, 2, 5.
Okay, 6, 9, 3, 1, 2, 5. Does everyone see that? So there's a way for us to. Can someone tell me if there is any pairwise communication that is not possible in this tree? Pairwise communication means communication between a pair of nodes. Can you think of a pair that cannot communicate on that spanning tree?
They're
Okay.
all connected through 1. So.
Yeah, so they're all connected through 1, so it's possible for any pair to communicate, right? Now here's a question. Are there other spanning trees that we can build on this graph? So so spanning trees are not necessarily unique. Does everyone see that? Okay. Any questions about spanning tree? So Why do we care about spanning tree? It's because we want to be able to enable any pairwise communication in the network. That's why we care about spanning tree. How do we compute spanning trees on a graph? You could run any graph search algorithms. Did you study, let's say, depth first and breadth first search? What do these algorithms do? Let's start here.
They're both algorithms
Mhm.
for searching out other nodes from a given starting point.
Yeah. So let's say the starting point is 1. In which case, let's say if we're running a breadth first search algorithm on this graph, we'll just expand out the first set of neighbors, and then we would go to those neighbors and expand their neighbors and so forth, right? So is everyone convinced that we could run the search algorithms that we learned, I think maybe sophomore year or freshman year, I don't know when. When did you learn about these algorithms? Breadth first search and depth first search. Or what's the name of the class? Data structures. Okay, good. So we can use those algorithms. How about Dijkstra's algorithm? Have you heard of Dijkstra's algorithm? Yeah. Could we use that algorithm to find a spanning tree, for example? So there are many algorithms. I'm just giving you some examples. And finally, it's important to realize that in networking, not only do we care about spanning trees, but also minimum spanning trees. Why might that be the case? Why do we care about minimum spanning tree? For example, we could come up with many spanning trees here, and one or some of them will have the minimum number of edges. That's called minimum spanning tree. A spanning tree with this spanning tree that you could construct with the minimum number of edges. That's called a minimum spanning tree. How many edges are there on this red spanning tree? 8. Okay. So could you come up with a spanning tree that has more than 8 edges?
Yeah.
How would you do that? Anyways, you could, right?
Yeah.
Pretty sure.
Yeah.
Okay, good.
Well, the URL says minimum spanning tree,
Yeah, okay.
assuming there's a max also.
Yeah. All right. So why do we care about minimum spanning tree? So we all understand why we care about spanning tree, but why do we care about minimum spanning tree?
The cost of sending something can only be measured in how many hops you have to make.
Okay, cost of sending something can be measured in how many hops we have to make, and hopefully minimum spanning tree allows you to do small hop communication. I'm not going to say minimum hop, but maybe small hop communication, because clearly the path between nodes 6 and 5 on this graph, that's not so short, is it? No. Okay. Any other reasons why you might care about minimum spanning tree?
Buy less wire.
Yeah, buy less wire. Right? If we could come up with a spanning tree, let's say that has 10 edges, we can, versus 8, it would cost less to deploy a network with 8 segments of wire. That's the idea. And so we care about minimum spanning trees as well. Okay, now let's go back to this example that we presented earlier. We have a LAN with a few bridges and a few segments that we showed earlier. So our goal is to construct a spanning tree that spans all the hosts in the network. And why are we doing this again?
Minimize the loop.
Yeah, or get rid of the loops if we can, right? That'd be another reason why we want to use spanning tree. There is one key difference between the search algorithms that we learned about, that we studied in data structures course, and this particular setting in which we're trying to compute a spanning tree. What is the difference? In the spanning tree that we studied earlier in previous courses, we assume that when we start running a program, we have a list of edges, we have a list of vertices, right? That means we've collected all the information from the network in one place and we have everything we need. We just process that list of vertices and edges. But when we have a network, we can't necessarily assume that, because these bridges are deployed in different buildings, the links go up and down, and for various reasons we've decided to build this network in a distributed fashion without a centralized controller. In that case, we need to be able to compute the spanning tree using a distributed algorithm. What that means is each bridge only knows about certain information related to the bridges that are in the neighboring areas, or even more precisely, adjacent bridges. For example, we have various bridges in this network, right? When we have a centralized algorithm that computed a spanning tree, we could assume, okay, here is bridge 1 and here are the neighbors of bridge 1, right? But when you're running a distributed algorithm to compute a spanning tree, we can only assume that a bridge can exchange information with its neighboring bridges. That's the only thing that a bridge can do anyway, right? So you need to be able to construct a spanning tree just based on those exchanges. So that's the difference between the spanning tree that we computed, or that we learned about or studied in previous classes, and what you need to do to compute a spanning tree in a distributed setting. Again, it's true that you could build these networks in a centralized fashion, but let's think about how we might compute the spanning tree if we build these networks in a distributed manner, which is how most of the networks are built today. For example, we don't install a controller if we just want to install some switches in our network, right? The switches have to be able to prevent these loops by computing the spanning tree themselves. In a more enterprise setting, we might actually have a centralized controller as well. So what's the goal? We want the bridge with the smallest ID to be the root. The root of the tree is the node at the top that connects all of the branches, right? And why the smallest ID? Why do you want the smallest ID to be the root? First of all, you all understand what that statement means, right? So let's say we have lots of bridges. What's the bridge with the smallest ID in our example? Let's say these are numerical IDs. B1 is the bridge with the smallest ID. Why do we want that bridge to be the root? Any ideas? It's an arbitrary decision. You could say bridge with the largest ID to be the root. That'd be perfectly fine. But the strategy has to result in a unique bridge. That's the key requirement, not the smallest ID. Of course, that's the convention that we use, not just in this protocol, but in many other network protocols that we might design. So fundamentally, smallest or largest doesn't matter. What matters is when all the nodes in the network run this algorithm, it should be the case that there's only one node that thinks it's the root. That's the key requirement, not the smallest ID or largest ID. It turns out smallest ID or largest ID happens to be a way to get to that requirement. Okay? All right? Each segment has one designated bridge responsible for forwarding its packets towards the root. So why do we want only one designated bridge? What happens if there are two ways to get to the root?
Isn't it the same as a loop?
Yeah. Then we have a loop. Right? The whole point was to make sure that we have a spanning tree with the minimum number of edges. If there are two different ways to get to a node, what can we do to make that spanning tree have fewer edges without disrupting connectivity? We can get rid of one of those edges, right? Because we're saying there are two ways to get to the root. That means even if we remove one of the links, we're still able to send a packet to the root. Bridge closest to the root is the designated bridge, because you might be connected with different bridges, and one of those bridges might be many, many hops away from the root versus the other one, right? In which case you should pick the bridge that's closer to the root as your bridge. Okay? And if there is a tie, it could be the case that you're connected to two bridges at equal distance from the root. Before we get to this point, what do I mean by distance? This means number of hops, number of segments that you have to go through. Right? That's distance. You could come up with other definitions of distance, but that's the definition we're using in this class. Okay, so slide says if there is a tie, bridge with lowest ID wins. If there are two bridges and they're equal distance from the root, then which one do you pick? The bridge with the lowest ID. Okay, here's a trick question. So why the lowest ID?
That's the number scheme we chose. The smallest edge is the root.
So
Yeah.
one of them's going to be smaller.
We have to pick one, right? All right. There's an interesting property to this particular choice. I don't know to what extent it's true, but it might be, which is, let's say the root bridge dies. In which case, if you pick a root with the lowest ID, maybe that would result in fewer disruptions.
The next root's going to be one of those
Smaller ones, right? One of the nodes with the smaller ones. If you are always picking if there is a tie, picking the bridge with the smallest node ID as your bridge, then maybe there will be minimal disruption if the root dies. Does that make sense? But it'll totally depend on what are the IDs that are distributed in the network, so on and so forth. But maybe in general that's true. I'm not sure.
Well, I think it would go the other way too. So if you're going to add new nodes here and there, normally when you add something, you increment the counter. You start with the minimum and then you go to count how many nodes are there. So you add a new bridge somewhere, you just add it to the end, but it's somewhere on the exterior.
Yeah. So it really depends on whether you have the ability to set the bridge ID, right? If you do, then maybe you start with 0. That's what you're saying, right?
Right.
The first bridge you deploy, you say, okay, ID 0. And the second one, you say ID 1. But you have to be careful there. You don't want to duplicate the IDs. A lot of times, these IDs come set in stone or etched on chips. All right. So here is a very high-level overview for how the algorithm works. So whenever we're talking about a distributed algorithm, we're talking about a program that runs on a particular node while interacting only with its neighbors. Right? You're allowed to exchange messages just with your neighbors. That's it. So a bridge is going to send a message, its own ID, and whether or not it is the root, it thinks it's the root, and distance from the root. It's going to send this message to its neighbors, and the bridges will receive a series of these messages through all the ports they have, right? And based on that, they can decide which bridge is closer. And based on your decision, saying, okay, I think, this bridge will get me to the root, with the least number of hops. I'm going to compute my distance and advertise that. All right, so that's the high-level overview of this algorithm. There is one other place where we studied a distributed algorithm earlier in the semester. Can you remember which one? It had to do with finding routes. For example, distance vector routing, right? In distance vector routing as well, ideally we're trying to find a tree with the destination as the root. All right. So what are some of the limitations of the bridges? The spanning tree algorithm doesn't scale, and broadcast doesn't scale. We need to use broadcast messages. And there is no notion of congestion, for example, in these kind of networks, right? We just know, okay, here's a way to get to the root, and you just forward all of your messages to the root if you don't know how to forward a message to a given destination. If we have network applications that assume a single segment, then the application might not work so well, right? Because we have a network with multiple segments, not a single segment. Makes latency between nodes non-uniform because depending on the path you take, depending on the tree that you build, you're going to have different latency, right? All right. So what we've talked about is, if a packet comes into a network that looks like this, how do we deliver that packet to a specific host? Right? Okay. Any question? And we also talked about if you want to send a packet to a node far away, first these packets have to get through internal networks. For example, you might have to know where the router is, right? You go through an infrastructure that looks like that to the border router, internal linear network, for example. And then it can start going through the internet. And any question about the link layer, local networks that we have in campuses? So in campuses, most of the time, I think most universities these days, they have what is called a star network. What that means is there is a big switch at the center, and there are smaller switches that fan out from that switch, and a lot of the hosts are connected to these switches, so you don't actually even need to run the spanning tree algorithm. Basically, you have a central switch, you fan out a bunch of switches, let's say in each building, and you connect hosts to the switches. But by accident, if we create a loop, we should be able to use the spanning tree algorithm to disable some of the edges so that we don't have a problem in our network. I think our campus also has a star network in the center of the campus. Any questions? No. All right, let's take a very quick break, and then we're going to talk about a physical layer.
Sorry, this might be a question that's sort of a combination of unclear and physical layer. So last time we were talking about media access and these various algorithms that we have. Now that is that something that still goes on with the current Ethernet standard? I mean, even though it's just two hosts?
Yeah, I think last time we talked about this, right?
Yeah.
I believe, for example, I think the gigabit Ethernet, I don't know exactly which one, there are multiple standards. They actually don't allow shared media.
Okay, I was going to say, are there any reasons other than the hassle of changing standards to not have, now that almost all links are just one
to the switch,
one to another,
yeah,
to change the physical standard to be something, to be a cable that has a dedicated connection each way?
I think it's just we have to get rid of all the devices that run those protocols. I think that's the
So it's just the hassle of
legacy
changing the standard.
Yeah, that'll be my guess.
Yeah.
It's just like that's a reasonable guess. Does everyone understand the question? For example, we talked about all the things nodes have to do to prevent collisions. But you know what we just mentioned is now a lot of the networks are shaped like a star, in which we have one computer connected with a wire to the switch. Right? And the switch is going to isolate different ports anyway. So why do we have media access in a wired network? In wireless networks, we still need that. In a wired network, why do we need that? And the answer might be, and we have a lot of these devices that actually use that mechanism, so we can't get rid of it. The newer standards, they actually don't allow shared media. And that's okay for newer standards because those devices haven't been built. Right? No one needs to go to the bathroom today? All right.
I guess the other thing was for the spanning tree, couldn't you make a version that takes into account a weight for each link, like latency?
You could. I'm not sure if that is done. Because in wired networks, we assume very low bit error rate. The links are high quality, that is what we assume typically.
Yeah.
And that's sort of true. So the difference between multiple links is almost immaterial. On a wireless link, it would be a different story. All right. Let's continue for a few minutes before we do the student presentations. So we've talked about how to send packet from, let's say, a node to another, or a node to a switch, so on and so forth. But eventually, this information has to be translated into something physical. Otherwise, we can't transmit information, right? So the physical layer is responsible for specifying, first of all, the physical medium. What kind of medium do we use to transmit information? For example, if we're talking about voice communication, what's the media that we use to transmit information? How is it that you can hear what I'm saying? With some medium, right?
Sound.
Air.
It's air, right? Based on what I studied, it's the compression in the air, based on what I studied. Similarly, we need some medium to transmit information. So the physical layer specifies that. Physical layer also specifies how we specify the signal, how we modulate. For example, we might use amplitude, or changes in amplitude, frequency, or changes in frequency to transmit something, which is the information. And finally, it also specifies how we encode the bits. Let's think about specifying the signal, or the signal that we transmit. First, there is this idea of chips, which is data at the physical layer. This is not the information that's coming from the upper layers of the stack, just the data at the physical layer. For example, the physical layer transmits some, or causes some change in the media, so that might be the chip. I'll give you a concrete example in a few seconds. And based on the chips on the physical layer that were received, we can interpret that as bits of information, which is what we provide to the link layer. So that's bits of information. It specifies the analog signal to chip mapping. For example, one very simple way we might specify this mapping is by saying, if there is a voltage of 0 on a piece of wire, then that's a 0. And if there is some positive voltage, that's a 1. So that would be one example to specify this mapping, a very simple mapping. We won't get through the details of the other one. Those are just names that you might want to familiarize yourself with. You don't need to learn the details. But if you hear the word FSK, for example, you should just know, okay, this is a way of specifying the analog signal to chip mapping. Have you heard of the word modem? What does modem stand for? Basically, it's a device that can modulate and demodulate information, right? So what modulation entails is changing the digital signal to a form that can be transmitted in the medium that we have, specified as the one that will carry information from node A to node B. That's what a modem does. So all the media, they're going to have some property that will determine how much information that you can send on this media at a time, right? That's called bandwidth. More precisely, it's the frequency that a channel can propagate well. For example, a channel might propagate all the frequencies, but it's going to propagate in a certain frequency range much better than some other frequencies. So that's the idea of modulation. You try to cause changes in the medium. For example, if I'm speaking, I'm moving the air molecules, right? Okay. As we said, depending on what media we are using, it's going to transmit some frequencies well and some other frequencies not so well. Right? This is something that we observe all the time. Right? For example, depending on how we've tinted our glasses, it's going to transmit some frequencies well and some other frequencies not so well. Right? So just a physical property. So we're going to use the carrier signals, basically the signals that are going to propagate well in the medium, but we're going to tweak them in some ways so that we can actually interpret these variations as information. That's what we're trying to do. For example, the very simple scheme that we talked about earlier, on-off keying. So let's say our media can propagate this type of signal very well, so that's what we're going to use. That's going to be our carrier signal. And if we want to use the fact that the signal exists and signal does not exist at a particular time to encode information, then it's pretty simple. Whenever we need to transmit 1, we're just going to transmit that carrier signal. And whenever we need to transmit 0, we're not going to transmit anything. So that would be on-off keying. We could also change the amplitude of the signal to encode different types of information. For example, 1 could mean larger amplitude. 0 could mean just smaller amplitude. Right? You could change the frequency of the signal, the carrier signal, to encode different type of information. For example, 0 could mean higher or lower frequency in this case.
Higher.
It's higher frequency. Why is it higher frequency?
It occurs more often in the same time interval.
Yeah. So if you look at, let's say, value, let's say this is value k, right? The signal actually has that value more frequently when we're transmitting 0, right? So it's higher frequency. And we could also shift the phase of the signal to encode the information, right? So now we know we can use the variation in the signal to encode information. The question is, how fast can you really do that? Why do we care about how fast we can change the signal to encode information? Because
what controls bandwidth.
Yeah, because that is going to determine how fast we can send information that we need to send, right? So it turns out it depends on various factors. First of all, the bandwidth of the channel. But it also depends on what is called signal to noise ratio. Because some channels are going to be noisy. And if the channel is noisy, it turns out we can't transmit information as fast as we can if there's a different channel that has less noise. Have you experienced this in real life? So what's a noisy channel versus not so noisy channel when it comes to voice?
If you're like in a stadium, it's really noisy and it's hard to get
Yeah.
what you're saying to the person close to you, as opposed to in here where it's not that noisy.
Yeah, it takes longer, I guess, if you wanted to stretch this analogy to that setting, right? You don't need to remember this formula, by the way. This is just showing, for example, if you have a channel with high bandwidth, you'll be able to send more information. We can just look at the proportionality. If the signal to noise ratio is high, can we send more information or less information? If the signal to noise ratio is high, can we send more information or less information for a given bandwidth?
More information.
More information. Does that make sense or no? So what does signal to noise ratio being high, what does that mean? We don't have a lot of noise, right? What if there's a lot of noise?
It's hard to detect what's actually being said.
Yeah. All right. So let's say now we know how to modulate a signal, right? We know how to modulate a signal because that's what we talked about. And we also talked about how quickly we can do that. The next thing is, how do you interpret these modulations? Or if you have information, how do we actually encode that into chips? And the difference is going to be clear here. For example, so actually this example still does not make that clear because there's still a one-to-one mapping between chips and the bits we want to send. So this is a very simple scheme. Whenever you need to transmit 0, you transmit it as low. And depending on the modulation scheme, that might translate to various types of modulation, right? So you transmit at 0. Whenever you need to transmit 1, you transmit that as high. Just think of low and high as two distinct points in modulation. So this is very simple. Any question here? No. Okay. What are some of the problems with this particular way of encoding? Let's say we're talking about straight low and high voltage. Let's say I want to send 5 zeros. What is the potential problem? I might lose track of how many zeros I've received, right? Let's say I send 100 zeros and 101 zeros. It's easy to lose track, right? I would just leave you with that. Here are some other problems. You can read them on your own. For example, baseline wonder problem. For example, if I transmit a lot of ones, what could happen is it could raise the voltage of the hardware that's responsible for modulation and demodulation. Because we're putting this voltage, high voltage, for extended period of time, for example. Right? All right. Is that the only way to encode information? No, there are other ways. For example, we could do non-return to 0 inverted. Encode 1 with transition from current signal and encode 0 by staying at the same level. For example, if we transmit 1, if we want to transmit 1, let's say if the previous transmission was 0, then we transition to 1. And if we want to transmit 1, but if the previous transmission was 1, we transition to 0. That makes sense? So anytime there is a transition, that's a 1. Or to flip it around, every time you need to transmit a 1, whatever you are transmitting, just flip it. Okay? So that's one way to transmit information. So here still there is one-to-one mapping between the bits and the chips. But here's something different. For example, in this particular scheme called Manchester coding, you map 0. Let's say you want to transmit 0. You actually map that to 0, 1. Just look at the first cell. You want to transmit a 0, but you encode that as 0, 1. And if you want to transmit 1, you encode that as 1, 0. So do you see the difference between bits and chips now? Chips is the information at the physical layer. Bits is the information that the physical layer provides to the upper layer. Because the information that we care about, it's that is 0 or 1, but we happen to transmit that as multiple bits, if you will, at the physical layer. Does that make sense? Great. How does it solve the baseline wander problem? Baseline wander is basically if you apply certain voltage on the wire, let's say we're talking about on-off keying type scheme, after a while it'll be hard for you to tell which one is high voltage, which one is low voltage, because you're applying that voltage for an extended period of time. The only way to solve that is by making sure that
2 zeros in a row is still on like an off-on.
exactly, yeah.
So you're always changing the voltage.
Right, you're always changing the voltage, and that's how you solve that problem. All right. And here's another encoding scheme that'll have a different number of bits and chips. Okay, so what are the goals of encoding? Well, we want to do DC balancing so that we don't have the baseline wander problem. We would like to recover from some chip errors, right? For example, or at least detect it. For example, we're using Manchester encoding, and let's say there is no transition, then we sort of know that maybe there is something wrong, right? We want to constrain analog signal patterns to make signal more robust, because the medium that we pick might transmit certain type of pattern more robustly than others. And there are some other goals that you can read about more. And here's the final example on encoding. For example, in this particular radio, if you want to transmit, let's say, 0, 0, 0, 0, let's say that is what we want to transmit using that radio. So that's the chip sequence that we use. So do we have a higher, is the bit rate higher than the chip rate? Or is the chip rate higher than the bit rate in this case?
The chip rate's higher.
Chip rate is higher. Okay, good. Now, if we increase the chip rate by a certain amount, will the bit rate go up? Yes, it will, but not the same number, right? And how are these ones and zeros on that we indicate on the chip? How are they actually transmitted in the physical medium? That depends on the medium that we're using. That depends on the modulation scheme that we're using. And does that 1 and 0, does that necessarily mean high voltage and low voltage? No. Depends on the modulation scheme we're using, right? All right. finally, we know how information, discussed very briefly at least, how information is carried in the medium, how we might cause some change in the medium so that we can interpret that as information. We also discussed the difference between things that you might do in the physical layer and how there might not be one-to-one mapping to the information that we're transmitting. For example, one piece of information that we want to transmit might translate to 4 pieces of information at the physical layer, or vice versa maybe, right? Okay.
So that's why wireless is so much slower, because in order to do the error checking, you've got to send all the extra overhead.
Or to be robust to errors.
Right.
Yeah, we're gonna talk about wireless networks starting next lecture. But to be robust to errors, these encoding schemes are designed so that even if there is a little bit of error, you can actually recover the bits. Because you know what the chips are supposed to be. And the chips are different enough that if there is just an error, a small error, you can guess where the chip should have been, or what it should have been. Does that make sense? So finally, we need to be able to say, okay, this is the beginning of the packet and this is the end of the packet. That's the final problem. We know how we can encode information, we know how we can transmit information, but how can we tell, what is the beginning of a packet or a frame and what's the end? Any ideas? Because we need that, right? When someone is speaking to you, how do you know what's the beginning and what's the end?
Usually they stop talking.
Okay. Okay, usually they stop talking. And how do you know it's the beginning?
They start talking.
Sorry. It was silent before, and now it's not silent.
But how about in a crowd where there's constant talking going on?
Oh, say your name. Maybe.
There might be some cues that tell you, okay, maybe I need to start listening to maybe this particular person, right? There might be certain patterns that we transmit on the medium that tells the receiver that, okay, the packet is about to start, or the frame is about to start. Those might be called preamble. Yeah. So we might send some sequence in the beginning, a unique sequence that indicates that we're about to send some information, we're about to send a frame. It's usually called a preamble. Once the receiver receives the preamble, then it can prepare its machinery to receive the actual packet. So you receive a preamble. Okay, now you know that you're about to receive a packet. Then you also need to transmit the length. Usually, I guess it's here, length-based framing. And once you know the length, you know exactly how long you're supposed to receive. Right? So that's how the information is framed. Physical layer receives it, and it can actually send it to the link layer processing. All right, any question? We did a very whirlwind tour of physical layer, but we don't have a lot of time for this topic. But I hope you got at least a general idea, at least a high-level idea for how it works. So we've gone from talking about applications and sockets to ensuring reliability using transport protocols, for example, finding paths across the internet, thinking about how those packets might be delivered inside a network when different hosts might be connected on different segments, and finally, how information is physically transmitted to the ultimate destination. That's what we talked about. All right, so we're going to stop recording and do some student presentations.